Good evening, everyone. I hope I'm audible. I'm Suyash, and I'm going to be talking about tactile friction under boundary lubrication. Just to re-emphasize, I'm a student under the supervision of both Professor Sanjeev and Professor Bobji from Mechanical Engineering. Friction has been studied for quite some time now. In fact, the first documented evidence of friction dates back to almost more than 500 years ago from the Da Vinci's notebooks. And after that, we've come across a lot of models and theories of friction. A lot of big shot scientists have had their take on it, and still till this day, the research keeps on going. But we still find ourselves in the dark as to what the cause for friction is. However, there are a uh, few common grounds that these theories develop, and the primary one is that the primary one is that we agree that friction is a force that resists the tendency of motion while there is sliding contact between the two bodies. All of these theories that have been mentioned in this slide, they present us with certain parameters that help us effectively modulate friction in various contexts. The important ones are roughness as it affects the contacting conditions between the two bodies, that is, as it affects the deformation or the actual contact area, which is quite key in controlling or understanding friction. But the important one or the focus of my today's talk would be lubrication, where you have a third intermediate species intermediating the contact between these two bodies, effectively changing the surface energy of the interface that is under contact, and adhesion, which is the primary or the rather important mechanism of friction in our particular case, is highly susceptible to change in lubrication. When we talk about lubrication, so Strybeck curve is a curve that is used to ascertain the regime of lubrication that we are in. It uses the film thickness to quantify the regime or the important parameters that determine friction in our particular case. If we reduce the film thickness where we have a molecularly thin film, uh, we are uh, we are under boundary lubrication regime. Just to re-emphasize, the film is molecularly thin, so bulk properties like viscosity and other properties like pressure difference don't really matter here. The sole properties which affect friction in this particular case are the interfacial properties. So anything that would be present on the interface has a potency to change friction in our case. And the characteristic uh, the characteristic thing is that out of all these properties, out of all these regimes of lubrication, it has the highest coefficient of friction value because much of the asperities are directly into contact as opposed to maybe thick or hydrodynamic film lubrication. So it is the molecules that are resolved onto the interface that are providing for lubrication and not the bulk properties. The system that we are trying to study in summary is it's a hard and soft contact under sliding condition, being intermediated by a molecularly thin film as opposed to a conventional thick film lubricant that we are much more used to. And we're trying to study the friction in this particular system, which has a lot of applications in different fields. So one particular umbrella is tactile friction, where the study of such nature can be help in designing products like haptic devices, where the finger sliding on a touchscreen surface is again falls under the same system. Then the compatibility of prosthetics with damaged tissue. Then some products where the feel is quite important, like some of the FMCG goods like creams, detergents, soap solutions, comfort of your fabric or clothes, or the mouthfeel of certain products, of food products. And systems where you have tissue damage owing to some biological or rather medical operations like a needle piercing your skin, where the needle is the harder body, or processes or procedures like endoscopy, where you have a probe which is much harder or stiffer as compared to your tissue against which it slides. Um, to measure friction, we have designed an in-house sensor which works on the principle of strain gauges. It is capable of measuring both the normal force as well as the tangential force or the frictional force simultaneously and independently To perform the experiment, we take about 10 microliters of the respective lubricating solution. We pour it on the top plate. We perform the reciprocatory motion, that is back and forth, for about 30 seconds. We repeat this procedure for 15 times, that's the set protocol in my particular case. And then we repeat and do the post calculation. We ensure that after an experiment, the cleaning is done via alcohol to get rid of any organic residue or any impurities, and drying of the finger is a must before we move on to the next measurement. The operating conditions, the important ones being the normal load and the reciprocating speed, in this particular setup are controlled manually, and the values are quite low, which are characteristic of tactile experiments. So this is the schematic of the entire process. What you see on the left side is somewhat of my final result, that is the frictional force represented by the blue graph, and the normal force, which is represented by the orange curve. However, another way to visualize the friction data in this particular case would be to view it as frequency or histogram plots. Since I'm doing we are doing the measurements back and forth, so we can ascribe positive value to one direction, and as we move back and forth, so the friction value changes from positive to negative intermittently throughout the measurements. The benefit of viewing the data in such fashion is that we are able to see a lot of noise and deal with it before we proceed on to make use of this data. And the main, so this is the characteristic friction force versus sign, how I would capture over an experiment. So the two main problems with the data are as follows. So the first one being the asymmetry between the two peaks, which is indicative of a bias in the sensor in one particular direction, which is obviously not desirable. So, and it's an inherent problem with the strain gauge mechanism. So, what we simply do is we simply subtract the drift that is quantified by the red line from the data to correct for this asymmetry between the two peaks. And then the second problem is standard deviation, or the spread or scatter of the data. So, as we can see on the slide, that we have this decaying sort of profile. It reaches an asymptotic value towards the latter part of the experiment, and we aren't really interested in that decaying portion. So what we do is we can simply truncate off the initial portion to focus on the asymptotic value, which gives us a better control over the standard deviation. After both of these steps are employed, we fit two Gaussian peaks on the post-processed data and capture the mean and the standard deviation, which help us put some statistical limitations on the data. So the evolution of coefficient of friction for the different contacting conditions in my case. So this is the coefficient of friction versus time plot that you would expect for dry condition, where it's just your finger. So most of the experiments that I've done, they are between finger and a glass slide with some respective lubricating solution. So this is the result for dry case, where much of the asperities are directly into contact. However, if you add water, you see the decrease, but the magic really happens when you add a surfactant solution. So if you compare the third graph to the first, the decrease is quite obvious, and at this point, we believe that it is this molecular assay present on the interface that is really doing something special. However, these are at this point merely models or hypotheses. We don't really know at this point if the arrangement of molecules is in this particular fashion as has been represented. But these models are pretty common in literature. So, so to explore different kinds of molecules, we had different classes like water, polymer, salt solution, surfactants. The details have been mentioned in the slide, and we do see that we get a great spread of data. But the interesting thing is that the interaction mainly falls in two categories. So first is the flat kind of profile, which you would expect for molecules that are just present on the interface, affecting the adhesive contact between the two bodies, like water or polymer. However, the decaying sort of profile, which I was talking in the previous slide, that is much more characteristic of molecules that have some dynamic nature to it, like surfactants, which have a propensity to get absorbed, or soda, which might be reacting chemically with the human skin. So different kinds of molecules are affecting coefficient of friction in different kinds. So we wanted to take a look at it in a more simplistic way. So we chose three surfactants having the same tail group but different head groups, and we measure the coefficient of friction. So as you can see from the right graph, for comparable normal loads, we did get a spread between the three different surfactant solutions. However, the interesting thing about this results comes out only if we start to look at the molecular structure of the surfactant molecule. So since we know it's an amphiphilic molecule, there's a parameter called the HLB parameter, or the hydrophilic lipophilic balance, which quantifies the size and the strength of the hydrophobic to hydrophilic interactions within the same molecules. And if we plot the coefficient of friction values that we have obtained for these particular surfactant solutions and plot it against the hydrophilic lipophilic balance, we do get a correlation. At this point, it's very early to make definitive conclusions out of it, but we do believe, since HLB value quantifies in some essence how the molecules are interacting with the surface based on the hydrophobic or hydrophilic ways. So we do affect that. We do think that it impacts the way the molecules are getting arranged. And as I mentioned in my first slide, that anything that can change the conditions, the contacting conditions on the interface, can change the friction. And we would like to take this study further. So in conclusion, I would just like to say that friction in my particular case is a function of both the substrate properties, which was roughness, which I didn't highlight in particular in this case, as well as the molecular properties, and any particular change, or rather anything that affects the interface, should affect friction. That's all.